Welcome everyone to the last day of the event, and today we have Shen Li, who is an associate professor at UW-Madison. She holds an affiliation with the Wisconsin Institute for Discovery and is a senior principal investigator of Institute for Foundation of Data Science. The core of her research is numerical analysis and scientific computing. And today she's going to present a talk on kinetic theory and data science. And she asks the question, who feeds whom what?
Okay, so it's my great pleasure to give a presentation on my perspective of data science. So my perspective of data science might be slightly marginalized. My research area is really kinetic theory. So what I would like to discuss today is the relation between kinetic theory, so this is kind of my background, and the relation between kinetic theory and the many subdisciplines of data science. In particular, I would like to ask the following question: how does kinetic theory and data science interplay? So this is a talk sort of target at a broad audience. I would like to I would like not to discuss the technical details, but rather to give a couple of examples. How do we apply kinetic theory to solve data science problem, and vice versa? How do you use data science techniques to solve some kinetic theory problems? So I myself come from UW-Madison, and this class of work is collaborated with two of my students, Ji and Dean and Shi Chen. Steve Wright is my collaborator and my colleague at UW-Madison. Okay, so let's start. If you haven't heard of kinetic theory, that's normal. Kinetic theory is kind of a subcategory of PDE. So what is kinetic theory? Kinetic theory is basically the following. Suppose you have a box of particles, and all these particles, they interact with each other. So in order to describe the dynamics of these particles, there are following two ways. The first way is to say, I just trace the trajectory of each particles. X1 is particle 1, X2 is particle 2, etc. So the particle 1 get moved around, so this is a particle 1 in time dynamics. This dynamics is controlled by the interaction between all the other particles. In some sense, let's say this is particle 1, and particle 1 can sense the force from some other particles. Other particles give this particular particle a force. Let this force drive this particle to go into a certain direction. And then I trace the trajectory of the second particle. Let's say this is the second particle, and its trajectory is given by the interaction between this particle with all the surrounding particles, etc. So suppose I have n particles, then I list n particles over here, and I trace the trajectory of all these n particles. The right-hand side tells you how they interact with each other. So it's a list of ordinary differential equations describing the trajectory of particles. So that's one way to describe particle dynamics. Another way to describe particle dynamics is the PDE, partial differential equation. So over here, instead of tracing the trajectory of each particle, I simply neglect the differences between the particles. I view them indistinguishably. And instead of tracing the trajectory of each particle, I write down their distributions. So this distribution is a distribution of time and space. Basically, I'm counting the number of particles at a particular time at a particular location. So suppose in the previous setting, I have n particles over here, and each particle is located at a specific location. Then I put the delta function on each particle and I sum it up. That becomes my distribution. So now the distribution of the particles need to evolve instead of each particle trajectory. And the distribution itself satisfy, instead of an ordinary differential equation, the distribution satisfy a partial differential equation. Its time devolution, its time dynamics get governed by, on the right-hand side, you have an operator. This operator acting on this distribution gives you the dynamics of the distribution. So immediately you see there are two different ways to describe the dynamics of particle. You can either write it as an interacting particle system using a list of ordinary differential equation, or you can write it as a distribution and you evolve the distribution. Apparently, the capital F over here as an operator of the distribution and the little f over here that encodes interaction between particles, they need to interact each other. So this capital F depend on the little f. Okay, so that's kinetic theory. Hilbert, back in 1900, he proposed a number of questions. And one of the questions he asked is the following. So he said that if you have one physical system that get described by different descriptions, then physics should be somehow unified. So you have two systems describing the same physical phenomena, then these two systems should have some intrinsic connection to each other. So this is called Hilbert number 6 problem. That is to link or find the mathematical equivalence between the description on the left and the description on the right. In some sense, we are trying to find out, as the number of particles goes to infinity, how does this description converge to the description on the right? Or how do you equate a list of ODEs with one PDE? So the core of kinetic theory the core or the aim of kinetic theory is to answer this Hilbert number 6 problem. Okay, so you may ask, where does this particle come from? So over here, I'm going to list 3 examples when people use kinetic theory in practice. The first example is the so-called Fokker-Planck equation. So this picture is taken at California Institute of Technology in Paul Ballen's lab. So in his lab, he studies the plasma. So he pumped plasma in this big tank. As you can see, there's a big tank. He put plasma in this big tank and imposed electric potential, and then he put a camera over here to observe how plasma interact with each other in the interior. The equation he write down is the following Fokker-Planck equation. So the left-hand side is the dynamics of the distribution. The distribution have the interaction of the distribution has 3 terms. As you can see, the time distribution get governed by 3 terms. These 2 terms on the left-hand side, it basically says, along the x direction, I move with velocity v. So x dot equals to v. And the second term tells you along v direction, v get accelerated or decelerated according to the electric field E. So translated to the ODE is x dot equals to v and v dot equals to the electric field. So that's the dynamics of the distribution. On the right-hand side, we have the collision operator. That is how particles really bump into each other and collide with each other and then change velocities, etc. So the right-hand side, usually we use a Fokker-Planck operator. So that's one way to describe plasma. Another example comes from the outer field. So this picture was taken by JPL. About a couple of decades ago, they sent a spacecraft in the outer space and take pictures of all the planets they see. And one of the picture is taken at the south pole of Euclides. It's number 6 moon of Saturn. As you can see, there's a plume over here. That basically means people found water in this outer planet. So when the news came about, people were excited. We found water in a different planet. This is an exciting thing. So the water vapor over here is described by the Boltzmann equation. So once again, this F is a distribution function. It tells you how many water vapor particles you can find at a specific time t, at a specific location x, moving with velocity v. So this is a distribution function, and this distribution function's dynamics get governed by two terms. So once again, the term on the left tells you the speed. Along the x direction, I move with velocity v, so x dot equals to v. And on the right-hand side, that's particles interacting with each other. So the water vapor particles interact with each other. It's a complicated operator, so let's not write it down explicitly. But you get the idea. So the Boltzmann equation is to describe the dynamics of particles. In this case, it's a water vapor particles. So the third picture is taken in Wisconsin. It's about 20 minutes drive from my home. So in the field, people set up the camera. So what they do is they send photons or they send light into sky, and they send light to the sky, and the photons get bounced back by the cloud, and they comes back, and you detect when these photon particles come back. And by counting the time it takes for the photons to come back, they can infer how much cloud is in the sky. As you can see, this is time from 0 o'clock to say about 2 o'clock, 3 o'clock. The cloud is gradually coming closer and closer to the ground. So we can imagine the storm is coming up. So when we talk about sending the photon light to the sky, this photon also is a particle, and the distribution of the photon particles get governed by this equation called the radiative transfer equation. So once again, this F is a distribution function. It tells you how many photon particles you can find at a specific time, at a specific location, moving with in specific velocity v. So this term, once again, is x dot equals to v. So particles move with velocity v in x direction. And this term is how photon particles interact with the cloud in this case. So if the photon particle meets the cloud, then it gets scattered around, and the scattering effect is encoded on the right-hand side. So all these examples are just to demonstrate that there are many particle systems in our world. It's either the plasma particles or water vapor particles or the photon particles. They get described by different equations, Fokker-Planck or Boltzmann or radiative transfer. But nevertheless, the format of the equation is the same. And this format, we call it the kinetic equation. So the distribution of the particles get scattered around, and the term on the left tells you how particles move, and the term on the right tells you how particles interact. T is usually the time, X is usually the space, and V is some problem-dependent parameter. And in our case, V is usually the velocity, but you can imagine in some other systems, over here, I call it the run tumble model from the bacteria, and multi-agent system from economy. And for this kind of systems, V has a different meaning, but nevertheless, the format of the equation still honor this form. So that's kinetic equation and kinetic theory. So what about data science? Another component of this talk is about data science. Many people, there are many people working in data science, many kinds of data scientists. So people's perspective of data science are usually slightly different. From where I stand, I think optimization and Bayesian are two components of data science. For example, in optimization, you have a loss function, and this loss function depends on the parameter. And one task in data science or one task in optimization is, can you find the particular configuration of theta so that the loss function is minimized? So that's one thing in optimization. Bayesian is slightly different. Bayesian takes a probability perspective. Instead of looking for one configuration of theta, it says all theta are possible. It's just some theta have a higher probability than the others. So in some sense, Bayesian is looking for the whole profile of the probability, but optimization looks for one particular configuration. I have a plot to demonstrate this. On the left, we have the optimization problem. So we have this is a contour of the loss function. We're looking for one particular configuration. And at this particular configuration, my loss function is minimized. And once you find this point, from the optimization perspective, the job is done. But Bayesian asks for slightly more. It not only asks for the point where the loss function is minimized or maximized, it also looks for the whole profile of the theta distribution. So this contains slightly more information. So in optimization and Bayesian, there are different algorithms that have been passed down to us from generations ago. For example, the gradient descent is a most straightforward optimization technique. Gradient descent says, I currently have one theta, and I know this theta is not right, is not the minimum point. So what I'm going to do is to descend according to the gradient of this loss function. If I walk in the right direction, there's a chance that in the future, I find a better point where the loss function is smaller. So that's gradient descent. And there are many other algorithms that are sort of based on optimization, some kind of a variation of the gradient descent. So let's ignore the discussion over here. Under Bayesian, there are a lot of algorithms developed in history as well. And one algorithm is the Langevin Monte Carlo, for example. It falls into the category of Markov chain Monte Carlo. Basically, you want to draw the samples according to this distribution. And one way to draw it is to use Langevin Monte Carlo. So there's a formula for that. And one can show that as n goes to infinity, you can claim that the theta is distributed according to the distribution over here, the target distribution. So those are all the jobs or the tasks in data science. So now the question is, on the surface, I don't know how you feel, but on the surface, I cannot really tell the relation between kinetic theory and data science. Data science asks for this either optimization techniques or the Bayesian inference, etc. And on the other hand, the kinetic theory looks for the particles interaction. So what's the relation between these two? So what I would like to argue today is that kinetic theory and data science, they sort of developed along their own trajectory. But recently they start talking to each other, and some kinetic theory techniques enter into data science and provide some good guidance to prove theorems, etc. And similarly, some data science techniques also entered into kinetic theory to help us understanding the kinetic equation better as well. So who feeds what? Let's see how data science get used in kinetic theory. Okay. So as what we said before, kinetic theory, you gave me the equation. This equation governs the dynamics of the distribution function. And I have the equation, I have the initial data, I have some boundary condition, etc. You prepare me all these things, and my job is to find the solution to the kinetic equation. So there are many perspectives you can take. There are many people working on kinetic theory, and they take different perspectives. Some people take an analytical perspective, some people take computational perspective. Analytically, we ask when the equation is well posed, has a unique solution, etc. And computationally, we ask, how do you compute this equation in a very fast manner? Okay. So kinetic theory has its own trajectory and has produced 2 Fields Medal already. So it's a pretty influential subcategory of PDE. So in the forward setting, we asked for solving the equation. And what I would like to focus on today is the inverse kinetic theory. So what do I mean by that? Let's draw the analogy to linear algebra. So in linear algebra, the forward problem is you give me the matrix, I multiply this matrix by the input, and I produce the output. So that's to compute the matrix vector product. So that's a forward problem. The inverse problem is to revert the process. There are two kinds of inverse problem. One kind is you prepare me the matrix, you prepare me the output, and I use the output and the matrix to infer for what's coming into the domain. So that is to reverse the process of the forward. So that's one kind of inverse problem. Another kind of inverse problem is slightly different. It's the second problem that we are trying to solve today, which is it is a matrix that is not known. What is known is you gave me the matrix input. I can take the measurement of the output. You give me a different input. I would have a different output. So if you prepare me a lot of input and output data pairs, hopefully I can use this data pair to reconstruct the whole matrix. So this is a much more complicated problem, but nevertheless, let's try to target on this problem. We're trying to use the data to reconstruct the operator itself. And in our setting, we are trying to say, suppose I gave the equation some incoming data, and at a final time, I take some measurement. Can you use this input and output data pairs to reconstruct the whole equation? For example, the electric field is not known, how the particles interact with each other is not known. I would like to use the data pairs to reconstruct all these parameters. So this is a summary. The forward problem is you give me the equation, initial condition, boundary condition, etc. I find the fast solver to solve the equation, to find a solution to the equation. The inverse problem is the reciprocal. I tell you the initial to the final data, and I would like to reconstruct the equation. Or I tell you the incoming and outgoing data, and I would like to use a data pair to reconstruct the equation, etc. So that's the inverse kinetic theory. So there are many examples of the inverse kinetic theory. Besides the example that we talked about earlier, we send a photon to the sky and count how many photons come back at a different time, so we can infer how much cloud is in the sky. So this is one specific inverse radiative transfer. And this is a picture you probably have seen, especially at the beginning of COVID. People are worried about the oxygen level in your body. So some people buy this equipment at home. So you put this thing on your finger, and it can detect how much oxygen, the oxygen level in your body. So what is happening over here is somewhere in this equipment over here, there's a small laser. It shines a laser beam to your skin, and it takes some measurement back. By this input laser beam and the beam sending back to you, you can tell how much blood oxygen level in your blood. So the core underneath it is also the inverse radiative transfer. We're inverting for the scattering operator in your fingertip. So the third picture is taken in a national lab, Oak Ridge National Lab. So what is happening over here is people shine laser beams to, this is a metal, aluminum, and aluminum is placed side by side with silicon. So what people want to do is you put this aluminum right next to the silicon, and you shine the laser to heat up the aluminum, and you detect the temperature change at the surface of aluminum. By this data pair, you can compute the heat transmission coefficient on the surface, on the interface between these two materials. The hope is that with the correct design of the combination of different material, we can design the material that has the best heat conductance, the heat properties that we hope for. So the underneath it is a phonon transport equation. Phonon is the particle people use to transport heat. So once again, this is the inversion kinetic equation. So inverse kinetic equation has a lot of applications. Okay, so let me summarize. We have a PDE, and in our case, PDE is a kinetic equation, and kinetic equation is parameterized by certain parameter theta. We send in some information and we collect some information out, and we are hoping to use this map that maps the input to the output to reconstruct your parameter theta. So the input there, as you can see, there are many different ways to send the input, and there are many ways to collect output. And once you have these data pairs, with the hope is to reconstruct the media information in the domain. Okay, so how does data science come into play for inverse kinetic theory? So for the inverse kinetic theory, as you can imagine, there's a question mark over here that we would like to infer. So the material is not known, but you want to infer for it. And what you can do is to collect the data sets. So very quickly, this problem falls into a PDE constraint optimization. So this L is an operator for the PDE acting on your solution equals to the source term, and the source term is the impinging parameters, impinging data. So you give me a source, I solve for the equation using this particular parameter, and I find the solution. And I measure the solution at the j's location. For example, this is my j's location. And then measure the solution at the j's location, and I hope this data matches with the data that you really do your experiment upon. So I take the differences between the detected, the PDE solution. I look for the differences between the PDE solution and the detected data, and I hope this data could match with each other as much as possible. So this is a PDE constrained optimization formulation. So there's one particular strategy in optimization called the stochastic gradient descent. And very naturally, this kind of formulation falls into the stochastic gradient descent formulation, because the loss function, as you can see, the loss function is a summation of a bunch of sub-loss functions. So very, very naturally, it falls into SGD formulation. Another thing that I want to say is sometimes you can invert this L into the right-hand side and move this U to here to eliminate the constraint. So you can change it to the unconstrained optimization as well. Okay. So this is a summary. So data science, there are many data science techniques, especially the optimization technique, the variations of gradient descent, for example, it targets at finding the optimization of the optimal point of a loss function. And these techniques can enter into the PD constraint optimization, and in our case, the inverse kinetic theory. So we have the difference between the data set and the PDE solution, and we want to find the parameter that gives you the best match. So these techniques could enter to help us solve this inverse kinetic theory. So let me summarize. Data science, data is naturally used to reconstruct the parameters in kinetic equations or kinetic models, and data science techniques can help us with the implementation or to really to execute this minimization formulation. So that's data science feeding kinetic theory. Okay, I would also like to discuss how kinetic theory feeds data science. So how do you use a kinetic theory to explain some techniques from data science? So on the surface, you wouldn't imagine that kinetic theory as a subcategory of PDE can be really helpful in understanding data science. So it's actually a little bit surprising that in the recent few years, there are some data science techniques that depend on interacting particles. And once you have the interacting particles, a lot of kinetic theory techniques could be useful. So let's come back to this optimization versus the Bayesian formulation. In the optimization, I want to minimize the loss function by performing, say, gradient descent. And in Bayesian, I'm looking for example, Langevin Monte Carlo gives you the sample that is drawn from the target distribution that you want. So both gradient descent and Langevin Monte Carlo, they are very, very classical traditional algorithms. There's no surprise over there. I'd like to argue, however, in the recent years, people find out that gradient descent and Langevin Monte Carlo, sometimes it only plays with one particles. For example, gradient descent, as you see, I move my particle from one location to a different location, and the new location presumably gave me a better loss function. But nevertheless, you're playing with one particle. The right-hand side is the same. I move my particle from one configuration to a different configuration by descending along, blah, blah, blah. So nevertheless, you're still moving one particle. So if you plot out the loss function, you're giving the trajectory of this one particular particle, and hopefully these particles can descend you to the minimum point. So in the recent years, people discover maybe, just maybe, one particle is not enough, especially in this case, apparently you have multiple minimum points. So why do you confine yourself in the setting that you can only have one parameter to play? So the argument over here is we want the collective information. Instead of having one particle changing from one configuration to another configuration, now I have a collective knowledge. A lot of us enter into finding the minimum point all together. So theta I is one particle, and I changing from one to, let's say, capital M. So there are a lot of particles, they interact with each other, and all of them explore the same landscape of the loss function. So that's a collective optimization strategy. So of course, this loss function needs to be rewritten from the original loss function. Similarly, under the Bayesian formulation, it's the same story. Instead of looking for one sample from the target distribution, we are now looking for a lump of samples all together. This I, there are so many of them, let's say 100, 1,000, 1 million, whatever. You have a lot of samples evolving at the same time. Because you have all these samples evolving at the same time, so samples could talk to each other and share knowledge with each other. So there's a better chance that you can find your local minimum or target distribution in a faster way. Is this true? I should say we don't know. We do not yet know if ensemble type method, either ensemble Langevin Monte Carlo or collective gradient descent, we do not know yet if this ensemble method behaves better than the classical one. This is something that we do not know yet. But we do know is under some situations, we can at least prove that the collective behavior of either the optimization algorithm or the sampling algorithm, the collective behavior at least get you to the right point. So the knowledge is accumulative. We gradually propagate, we gradually enlarge of the frontier of the knowledge, and hopefully someday we can finally say that one method is better than the other. We're not there yet, but at least for today, I'd like to show you two examples that ensemble method, at least it works. Whether it works better or not is a different story, but at least it works. So there's two examples. One is the parameterization of neural network. Neural network is a hot topic that everybody is excited about, but we don't really know when training of the neural network can guide you to the optimal point. So I'd like to argue today that if your neural network is over-parameterized, there's a very good chance that you can get to the minimum point. Another example that I would like to show today is the Bayesian inference. If you have a lot of particles sampled sampled down, there's a very good chance that the samples talk to each other and they finally reconstruct the whole distribution. Okay, so let's look at the first example, that is the overparameterization of neural network. So I believe all of you have a little bit of knowledge of neural network. So the neural network, the structure is relatively easy to say. We have an input X, and we go through many, many layers of neurons, and we have an output. The hope is that in reality, you can accumulate this X to Y map, and you'd like to train the configuration of these neurons so that the output of these neurons for this particular X would match the labels that you gave me. So there are many ways to design your neural network. For the moment, I would like to confine myself to the residual network. So the neural network, let's assume that the neural network has L layers. So it's a L deep. And in each neuron, in each layer, I have M, this many neurons. Each neuron is configured by the parameter theta. So the first subindex tells you which layer you are at. So this is layer 1 and 1. And the second index tells you which neuron for this layer. So it's theta 1 at 1, theta 1 at 2, etc. So the number of neurons is basically L times N, those many. L times M, those many. Okay, so for the residual network, this is the updating formula. You come in as ZL, and I update the solution ZL to the new solution ZL plus 1 by summing up the contribution of all the neurons at this layer. At this particular layer, theta is parameterized. At this particular layer, all this theta get parameterized by L, and there are M of them. This is the activation function. It tells you that from previous layer solution to the new layer solution, I need to add up the contribution of all neurons acting on this current stage. So what I would like to argue today is that if the neural network is over-parameterized, by over-parameterized, it means that we have a lot of neurons in your neural network. So it's over-parameterized. This L and M goes to infinity. So the size of the neural network is really big. And I would like to argue that if the size of the neural network goes to infinity, this residual network updating formula could be rewritten into the ordinary integral equation. So once you are changed from the discrete setting to the continuous setting, there are many tools that we can use, many ODE and PDE tools that we can use to understand this updating formula. So how do we do that? Let's imagine that this is your neural network. Initially you have 1, 2, 3, 4, 5, those many layers. And in each layer, you have 5 neurons. So in total, you have 25 neurons. Suppose I gradually elongate this direction. I have a lot of layers altogether. Then from far away, if you draw yourself far away, you don't really see they're basically equivalently distributed along this line. So from far away, it's kind of continuous, right? So it becomes a line of neurons with some dotted pearls along it. So this, we call it the continuum limit. So this is to send the number of layers goes to infinity. If the number of layers goes to infinity, you have a continuous flow of neurons. And then we can send the so-called mean field limit. That is to add, instead of having, over here we have 1, 2, 3, 4, 5 flows of neurons. Now suppose instead of having 5, we have a lot more flows of the neurons. So basically from far away, you cannot really distinguish one neuron from another. You have a whole map of neurons in front of you. And this is a so-called mean field limit. That is to send the number of neurons per layer to infinity. by sending both parameters to infinity, we are in the over-parameterized regime in the sense that we have a whole lot of parameters. And in this setting, the problem changes from the original discrete version of the neural network to the continuous version of the neural network. And now, instead of tracing the trajectory of each neurons, I'd like to trace the trajectory of the distribution of the neurons. So this is exactly the formulation that kinetic theory uses. Instead of looking for each trajectory of these particles, I want to take the statistical perspective and look for the evolution of the whole distribution. So this is when kinetic theory becomes useful in explaining data science. Okay, so previously to train neural network, we need to find the configuration of those theta, those parameters. Now, instead of training the parameters, we find the configuration or the dynamics of the underlying distribution, which is rho here. So the training of theta now becomes the training of rho. Okay, so as I previously said, the neural network, by sending L to infinity limit, which is instead of having finite many layers, you have infinitely deep layers. So you have basically a few lines of flows. In this setting, you translate the residual network to a class of ordinary differential equation. And then you have a whole lot of lines over here. So the ordinary integral equation get translated to the, ordinary differential equation get translated to the ordinary integral equation. So this is to pass a continuous limit and pass a mean field limit respectively. And once you pass the limit, instead of dealing with the discrete setting, you are dealing with a continuous setting. And this continuous setting happens to be a gradient flow PDE. And there are lots of techniques in PDE that we could use. So over here, we proved that the PDE converges to the minimum point. So you can gradually descend your configuration of the neurons so that you have exact match of the data and the neural network output. So I'd like to, so this is a relatively technical, but let me still just spend 1 minute on the result. So the result that we prove is the following. The number of layers has to be 1 over epsilon this much. Let's say epsilon is 1%. If epsilon is 1%, that's the accuracy you are looking for. If the accuracy you are looking for is 1%, then the number of layers has to be 100, right? And at the same time, the number of neurons per layer, so this direction, the width of the neural network, has to be epsilon squared. So in this case, it's 10 to the power 4. So you have 100 layers, and on each layer you have 10 to the power 4 this many neurons. If that is the case, I can claim that the loss function produced by the original neural network and the loss function produced by your limiting equation with high confidence, you are close to each other. So the difference between the two loss functions is only epsilon 0.01 this big with very high probability. So this is a probability bigger than 1 minus eta. Let's say eta is another 1%, for example, then you have 99% of the chance that the two loss functions are close to each other. So this is a pretty strong result. This is basically suggesting that in the limit, if your layer is truly a lot and the number of neurons is truly quite a lot, then you can indeed view the training of the neural network by the gradient flow PDE. And then you show that the gradient flow PDE in the training time going to infinity limit indeed converge you to the zero loss function. Please forget about the technical details over here. I want you to focus on this line. So this is to say, as the training time goes to infinity, the cost of the gradient flow, the loss function is truly descending you to 0. And when we combine this with the result over here, you can see that E of theta is also descending you to 0. So that basically means you indeed find the configuration of the neural network so that the output of the data really matches with the label that you gave me. So you find the optimal configuration. So there are a couple of results in this direction. We're mostly inspired by Chiat and Bach, who proposed using the mean field limit or kinetic theory as a toolbox to understand neural network. So the paper was accepted about 2 months ago. So that's one example. As you can see in this example, we use a kinetic theory, this interacting particle system, as a tool to explain some data science technique. And another example is to use a kinetic theory in Bayesian inference. As what we said before, the Bayesian inference is to find a target distribution, is to find particles according to the target distribution. Bayesian itself, it says, I have a prior distribution and I multiply with some kind of likelihood function and I produce the posterior distribution. U is a parameter and Y is the data. So you hope you can use your data to infer for the configuration or the probability distribution of the parameter U. So you have a prior distribution over here and you multiply with the likelihood that your posterior distribution. That's kind of the Bayes rule. So there are many algorithms using the Bayesian inference, including the Markov chain Monte Carlo, including Landry Monte Carlo, sequential Monte Carlo, etc. There are so many algorithms. What I would like to argue today is that there are some new algorithm is ensemble type that are also work very well. So the ensemble method works as the following. So instead of viewing it as a function, I draw samples according to the prior distribution, and I let the samples move around. If the samples get moved around, hopefully after some certain time, the samples can be drawn according to the target distribution. Since I have a lot of particles all together, they feed each other knowledge. So there's a good chance that I can achieve the target distribution in a faster manner. So now the question is, what kind of motion that you want to introduce to all these particles so that these particles can quickly recover the target distribution? And this is when the algorithm diverge. Different algorithms give different answers to what kind of motion each particle should follow. And what we can say today is that many of these algorithms would work. It's still a little bit far away to say that one method is better than the other, but at least we can prove they are accurate. So let's forget about the details. Let me just quickly summarize that. Let me forget about the details. The punchline is you have a target distribution which is represented by a function, and instead of drawing the function, you want to represent the function using the particles, and you induce some kind of motion. When you induce a motion, you have on the particle level, each particle sends the motion using the ordinary differential equation. And if you look at the whole distribution of the particles, it becomes a PDE. So it very naturally falls into the kinetic formulation. And now we use a kinetic formulation to connect ODE and PDE, and we say the PDE converge you from the prior distribution to the correct target distribution. Okay, so this is a little bit dense. Let me forget about the details, just to summarize. So kinetic theory, it basically gives you the recipe to say that a list of ordinary differential equations sensed by each particle is similar to the distribution of the particles characterized by the PDE if the number of particles goes to infinity. And this kinetic theory perspective sometimes can be really useful in explaining data science techniques. And we have shown two examples. In one example, we have the overparameterized neural network. And on the second example, we have the Bayesian inference and their algorithm called ensemble Bayesian sampler that can be explained using the kinetic theory. So I think I should wrap up. Kinetic theory and data science on the surface, they are different disciplines, but somehow underneath the surface, there are quite a lot of relations from one to another. All right, I should finish. Thank you.
Thank you very much, and this was great. It's great to see the interdependency between partial differential equations and data science, and your own perspective as well.
Yeah, thank you for the invitation. And data science is a pretty big community, so people take different perspectives. I would say my perspective is kind of marginal. Not a lot of people use this perspective, but I do think that sometimes it's complementary to the mainstream of to data science.
Oh, thank you very much. It was a pleasure to meet you.
And yeah, I see some comments.
Yeah. Okay.
Oh, that's okay. It's recorded anyway, so you can always go back. Yeah. Thank you.
Thanks, Jen.